Hello, I'm Ben, and in my 5 minutes, I'm going to talk to you about what happens to red supergiant model spectra when you include a wind. Now, the optical spectra of red supergiants are full of molecular absorption bands, in particular, absorption due to titanium oxide. And these spectra are difficult to understand using, for example, your standard Marx model atmospheres. Now, for many red supergiants, we can tune the effective temperature and the extinction to get a tidy looking fit in the optical portion of the spectrum. And the problem comes when we investigate how that fit performs at other wavelengths. And what we see is that a model tuned to the optical gets the near infrared badly wrong. Conversely, a model tuned to the near infrared gets everything right apart from the titanium oxide bands in the optical. So this leads to what is described by literally no one as a effective temperature crisis for red supergiants, which is that the temperatures derived from the optical are always much cooler than those that you derive from the near infrared. And specifically that effective temperature calibration of Emily Levesque, which is determined from fits of Marx model atmospheres to the optical, must then give you the wrong bolometric corrections and near infrared colours as a function of spectral type. So one possible solution is this. So we all know that red supergiants have winds, but all the widely used model atmospheres, for example Marx or Phoenix, have no wind included. So if we look at the schematic of a static model atmosphere as a function of density as a function of temperature, by adding a wind, what we do is we increase the density at higher altitudes in the wind and therefore at lower temperatures. So if we look at where the titanium oxide forms, by increasing the mass loss rate, we increase the density at the titanium oxide formation temperature. So onto our results then, and this is what we see. So if we compare a spectrum from a windless model in black, that always has weaker titanium oxide bands than those models with mass loss rates typical of red supergiants, even though all those models have the same effective temperature. But in the near infrared, the flux is largely unchanged. So wind increases the strengths of those titanium oxide bands without changing the flux in the near infrared too much. And if you're interested where that missing flux goes, it comes out in the mid-infrared in the form of CO and SiO emission between 5 and 10 microns. So what are the implications then? Well, obviously, firstly, we can now potentially reconcile temperatures derived from the near infrared with those from the optical. So this is work in progress right now, but it will result in temperatures warmer than that Levesque et al. Calibration. Now, secondly, a wind naturally explains the existence of so-called Mole spheres, or spatially extended regions around red supergiants which are responsible for at least some molecular line formation. And these can be seen in, for example, interferometric data of Betelgeuse, where the CO bandhead, which forms at 2.3 microns, which you can see in the normal flux spectrum in the top panel, that's seen to form at larger radii than the continuum, and that's shown in the bottom panel there. Now, if you look at what we see in our models, which we haven't tuned, this just naturally falls out when you incorporate a wind into a model atmosphere. This spatially extended zone, which is responsible for the formation of those molecular lines, is naturally reproduced by simply just adding in a wind of a garden variety mass loss rate. So to conclude then, by incorporating a wind into red supergiant model atmospheres, we can firstly reproduce the whole optical and near infrared spectrum with a single effective temperature. And secondly, we can naturally reproduce the observational features of red supergiants, which have up until now always been typically explained by the existence of these so-called Mole spheres. Thank you.